Okay, so today what we're going to do is we're going to start our new section on logistic regression. So that's part 8, chapter 33. And I think you'll find this section very useful. Logistic regression is used in many, many different situations. Basically, whenever you're what you're trying to predict, your y variable, is a binary variable. So it's a model for predicting all or nothing outcomes. So far, I don't know if you've noticed, but the y variable in all our predictive models have been quantitative. Our x variables, our predictors, have been categorical or binary, even like gender. But our y, what we're trying to predict, has always been quantitative. Exam scores, heights, GPAs, etc. But what if what we're trying to predict is just has two outcomes, yes or no, success or failure? It happens all the time. If you want to predict life or death, right? Pregnant or not pregnant, etc. And then we're trying to predict a 0 or a 1. And really the best we can do is predict the probability. Finding a model that predicts the probability of getting a 1, the probability of success for any given set of conditions. So here's an example of a data set where we're trying to predict whether people get accepted to medical school or not. So 1 is accepted, 0 is not, based on a bunch of different factors. And so let's look at, we have a data set in our in the data program that's we can look at in a minute. And one of the predictors is their score on the biological science section of the MCAT. And so this was a data set of 55 students randomly selected from a Midwest university. And so we look at this, and I have it right here, and you can pull it up too. It's on our data program, so we can take a look at it. And we can see, so let's predict, so our y variable is yes or no, and our x variable is going to be, for this one, is the biological science score. So this is 55 students. Let me put some scatter, some jitter around it so that you can see the students show up. Okay, so for example, there were 4 students, there's 3 up here, who scored a 12 on their biological science score, just 2 who scored a 6, etc. And there's a bunch of them here. There's a cluster of them. This is 55 points altogether. Now, these are all 0s and 1s, so if we do a regression, what would we be doing? Like if you look at this regression line, you can think of it as trying to fit like the percentage within each of these vertical strips. So for example, trying to fit these little horizontal lines. So this says of the 2 people who got a 6, neither of them got into medical school. The 4 people who got a 12, well, 3 got in and 1 didn't, so that 75% of them got in, and that little horizontal line is at the 0.75. So what we're trying to do is fit, if you just fit an ordinary linear regression, you're basically trying to fit the line that best goes through all those little horizontal strips. And clearly it's going to have problems because if you're thinking about predicting probabilities, it's going to extend beyond 1 and below 0. So you're going to get negative probabilities and probabilities greater than 1. So if you use this equation here, that's the first. Let's just go to our document camera, and we're going to use the equation. You'll see you get crazy stuff, so we can just do that first. And so we go to the document camera here, and we're just going to use this usual least squares equation, and it doesn't make sense, as you can see, because if you predict for somebody who makes for a 10, yeah, it's going to predict a reasonable probability. We can just do it. What will we get? We'll get the predicted probability of acceptance right here is going to equal negative 1.263 plus 0.1848 times 10. So we get 0.585 or 58.5%. Okay, so that makes sense, but look what happens when we do the same thing, use the same equation, and instead of doing this, we put a 6 in here, the same equation. Well, then we're going to get a negative probability, and you can see it right here. This line's going to extend down to negative probabilities. So you get negative 0.154 or negative 15.4%. And if we do the same thing for somebody who has a 14 and you stick 14 in there, you can see from the graph, we're going to get a probability over 1. So we got 1.432 or 143.2%. And that's nuts because, as you know, that, probabilities have to, so this doesn't make sense, this doesn't work. In the range we're even interested in because probabilities have to be between 0 and 1 or between 0% and 100%. So we're going to have to do something else. All right? So we can look at, so what we're going to do is not fit a line, but fit a curve. Okay? This logistic curve. So how can we fix this problem? I can show you again on the data program here. So instead, we can go to, you can play around with these different programs here. But here we can go to a 0-1 scatter plot and choose the same y variable of acceptance and the same x variable of biological science score here. And here is what we did before. We can add jitter too, so you can see how many people are in each category. And here, we did this, which was basic. So we're trying to fit these percentages here. Like right here, this is the percentage of people who scored. I just put little dots at those. We're trying to fit that. But we do a much better job if we do a logistic regression curve than if we do a curve. So let's look at what this curve is. So let's go back to the document camera. Excuse me. And let's think about this. Okay, so we want to fix this problem of getting these probabilities greater than, we want to bound this curve right here at 1 and 0, right? So we want to fit a curve instead of a line, and a curve that has this kind of S shape like this. So there's lots of curves that are going to do that. Basically, any curve of the form y equals some function, positive function, increasing function of x, over 1 plus that function of x will fit that. So now which one do we choose? So there are many S-shaped curves similar to this one, and the most commonly used one for this is the logistic curve, which is, and we'll explain why it's commonly used, but this is what it looks like. It's of this form, where the probability of success is e to some linear function of your x's. We only have one x. We're going to do multiple regression just the way we did with ordinary least squares regression, fitting a line. But what's going to happen is this linear, it's going to be linear in the exponents here. So with just a single x, today we're just going to start with a single x predictor biological science score. We'll later add more predictors, but it's of this form. So let's just make sure this, and we'll explain why this form's nice, but first let's just make sure that it fits, that it can't ever yield probabilities over 1. Can it ever yield probabilities? No, because, because e to anything is going to, ever greater than 1. No, because the numerator is less than the denominator here, right? So it's never going to go greater than 1. So that's because the numerator here is always going to be less than, you can see that, less than the denominator. So it's never going to be bigger than 1. And can it ever be less than 0? No, because e to the anything is, no, because e to the x is greater than 0 for all x. You know, the limit as x goes to, the limit of e to the x, I'll just write that way, the limit of e to the x as x gets really small, as x goes to negative infinity, is equal to 0. It can't ever get smaller. So we've got a nice function here. And it's particularly nice because we can transform it. The reason we want a function like this is because we can transform it into a function that's linear in x by doing, by taking what's called the log odds version of it. So this yields, this yields probabilities between 0 and 1. We just saw that. That's nice. And we can transform this variable. We can transform, see, it's linear in the exponent here, right? It's going to be linear in this exponent here. So we can do a transformation of this probability. We can transform this into a nice line. If we take the, first transform this into the odds equation, and then into the log odds, which will be in the exponents, which will just be this part of it right here. This part right here, the exponent. Let me show you how to do that. Okay? So we can transform this into this nice equation right here called the log odds equation. So, and it's linear in x, which is what we want, and then allowing us to continue using the methods we developed for linear models. So that's why we do this. So, so we have this logistic regression model that really just has 3 equivalent forms. 3 equivalent forms. You have this nice S-shaped curve here, this really pretty S-shaped curve in this that we just talked about. So it's going to look like it goes between 0 and 1. It's bounded, and it looks, it's some kind of S-shaped curve. That's supposed to be a pretty S-shaped curve, like that, between 0 and 1. All right, we've got that S-shaped curve. So this is an S-shaped curve. And then to transfer from, then you can do it in the odds form. So instead of probability, we can change it to odds, which is basically the probability over 1 minus the probability. So it's like the ratio of the successes to the failures. So we can transform this easily to this. And then, as you can see, it's still going to be, probabilities are always between 0 and 1. It's still going to be positive, but it's not going to be bounded by 1. It's going to be, this is going to be an exponential curve. And so this is an exponential. Here you have the S-shaped curve. Then we can change it to an exponential curve that will just be bounded between, at 0, but it can go to positive infinity. So it will look like this. It can go up to positive infinity, or it could go that way. But it can't get less than 0, right? And then what we're going to do is then we're going to take the log of that, the log of the odds, right? The log of the odds, and then we'll just have something that's a line. So it will be the linear form. So we go from an S-shaped exponential curve to just a line. And then we're just going to have a line that can go from negative infinity to positive infinity. And it's linear. And that's what this form is, the log odds form. So that's the idea. And you just through algebra, we can transfer back and forth. This looks really messy. It's super simple. We can look at this. I mean, we can go back and forth. Let's just do it in an example, and then this is just algebra, and we'll just do an example, and you'll see if you need to prove it. This just looks cumbersome. So let's just do it easily, just with numbers, and you'll see what's going on. Okay? So, so this is called the log odds form, right? And P over 1 minus P is the odds. So basically think of it as the probability of success. Success being, you can just define P as success, and then 1 minus P is going to be failure, right? So if your odds are 4 to 1, that means the probability of the event occurring is 4 times more than the event not occurring. So they call it 4 to 1 odds. So for example, let's say, this is just, okay. So here you have P over 1 minus P, right? So what is P? Let's call P the number of successes over the total number of outcomes. The number of total outcomes, right, that are possible. And then we'll call 1 minus P here just the opposite. We'll say the number of failures. If everything's either a success or a failure. All you can get is a 0, 1 outcome. So that's the number of failures over the number of total outcomes, right? So really, your odds could just be the number of successes over the number of failures, right? So if your odds are 4 to 1, what does that mean? So odds, I'm sure a lot of you who gamble know this like the back of your hand, but some people might not. So the odds of 4 to 1, the odds of 4 means what? It means 4 over 1, 4 successes. You can think of that as 1 failure. So if you want to change it to a probability, how do you do that? So these are your odds. If you want to change it to a probability, it's going to be the number of successes, 4 in the numerator, number of successes, over what? The total number of outcomes. What's the total number of outcomes? It's just 4 plus 1, or 5, right? So it's just, how about odds 1 to 4? What would that mean? Odds 1 to 4. What would that mean? It would mean 1. Another way to say it is 1/4. So then your probability of a success is what? 1 over 5, right? So that's where we're getting this from. Your odds, you know that the odds are P over 1 minus P, but the probability is odds over 1 plus the odds. That's all we're doing. Odds over 1 plus the odds. Okay? So if your odds are 1 to 2, right? So if your odds are half or 1 to 2, odds equal 1 to 2, then what's your probability? Your probability is what? 1/3. There's one way to succeed and 2 ways to fail. And if your odds are 2 to 1, then your probability is what? 2/3. Does that make sense? I mean, this formula is exactly the same thing. What if I translated 1/2? So this would be the same as, what if you saw it like this? 1/2 to 0.5. What if I said odds equals 0.5, right? Then you could say, okay, your probability is equal to, you might like to write it like that, and then you could say your probability is 0.5 over 1 plus 0.5. It's still 1/3. That's all we're doing, so you understand that. Right? Does that make sense to everybody? Okay. So that's the same thing as, this part right here. So if your odds are this is like, you could say, then this is odds over 1 plus the odds. You can go back and forth there. And you can just do it by algebra, but it's just very simple to see if you think of it that way. That's all we're doing. The probability is odds over 1 plus the odds. Okay, so now we've got that. And do we need to do this last one? Sure. So if your odds are 2 to 3, what's the probability? Probability is going to be what? 2/5 if your odds are 2 to 3. Does that make sense to everybody? All right, so this chart might help. So you'll see what we're doing here. So why don't we just quickly fill out this chart. And so we can start anywhere you want. Doesn't matter. You can just start right here. So let's say the probability was 1 out of 100. Then 1 minus the probability is what? 99 over 100. They have to add to 1. And now what's your odds? It's going to be this p over 1 minus p. And you can see that the hundreds will cancel out, so it's just going to be 1 over 99, right? Does that make sense to everybody? That's just p over 1 minus p. Questions so far? Okay. So, and then what are the log odds? I need a calculator for that. So, the log odds would be negative 4.6. Let's just round it. Negative 4.6. So this is, I just set it up symmetrically. So let's just switch it. What if your probability is 99 over 100? Then this is going to be 1 over 100. And then your odds are 99 to 1. And then instead of negative 4.6, it's going to be positive 4.6 for your log odds, right? So it's very symmetrical around 1/2. And look what happens at 1/2. Okay, when it's a 50-50 chance of something, 1/2, p is 1/2. 1 minus p is also 1/2. Your odds are 50-50, 1 to 1, 1 to 1. And the log of 1 is 0. So that's right in the middle here. And so as you can see that it's going to extend here, it can get, as we go from the probability getting smaller and smaller and smaller, it can't, at the limit it's going to be 0. You could get 0 is the smallest probability, and the biggest you can go in this direction is 1, right? Same with 1 minus p in the opposite direction. And the odds, as you can see, goes the smallest you can get in this direction is 0. But now you can see that it's going to go to positive infinity here. And with log odds, you can see it can go from negative infinity to positive infinity, mirroring those curves. And when you have a 50-50 probability, 50-50, 50% probability of something happening, it's going to, then you're going to have a your odds are 1 to 1, and your log odds are 0. So if you have negative log odds, that means you have less than 50% chance. Positive log odds means more than 50% chance. Less than 1 in your odds means less than 50% chance, etc. Okay? So if we look back at our curves, or maybe we should just do it, we could draw the curves here again, but it's kind of repetitious, isn't it? We could just go back here, where we already have it nicely drawn out. And we can just say, okay, so here, in probability form, if you have a 50% probability, it's going to go right there. And that's going to translate to a 50%, 50%, this is on page 173. That's 50% probability is the same thing as saying your odds are 1 to 1. So, and it's the same thing as saying your log odds are 0. Those are equivalent. All right. So any questions so far? So those are our 3 forms right here. And here's how we go back and forth between them. And now what should we do? All right, so let's make predictions using these log odds equations. Okay, so where are we going to get these predictions? Let's look at this. So we're back to the probability of our same example of getting admitted to med school based on your biological science score. And the computer is going to estimate these values for these 2 parameters, the intercept and the slope in this log odds equations. And it's not going to be doing it the same way as the least squares estimates that we've been used to. It's instead going to be obtained by doing something called maximum likelihood estimates, which is maximizing the probability of getting the data that you have. They're the same as the least squares in ordinary least squares. They're the same if you have linear regression, but they're not going to be the same here. We're going to learn more about it later, but let's look at page, we can just take a quick look. Where do I explain this? Okay, quick look on page 186, just for a second. We can think about it more, but first I just want to, we're not going to be doing inference now. We're just going to make sense of how to go back and forth between probabilities, odds, and log odds, and what the coefficients mean. But let's just quickly look here. And so the main difference between the ordinary and the logistic regression is how we estimate these parameters. So instead of minimizing the sum of these squared residuals, we're going to use this maximum likelihood method. We're going to maximize the likelihood of getting our sample data. And it's the same as minimizing the deviance. So we're going to look at these deviance tables that match up very nicely with the ANOVA tables, sums of squares. Let's see. I mean, I think you can see the reason why. Let's just go back to where we were. When we look, we just have a bunch of, okay, the reason why we can't use least squares is because we just have a bunch of zeros and ones we're predicting. And they are certainly not normally distributed around it just violates all our assumptions. We can't use, the maximum likelihood estimates are only going to be the same when we have normality of the errors, and we don't here. So they are, with your least, if you have normality of the errors, then yeah, the maximum likelihood estimates will be the same, but they're not going to be here. So, all right, now, so we get this this deviance table. We're going to look at this more later. It's going to be very similar to our ANOVA table, and this we're going to look at how the chi-square, some tweak on the chi-square statistic is the same as the deviance. All right? But for now, let's just say, okay, so we got these, the computer gave us these estimates, and now we have these slopes right here. And so here is our equation in log odds, okay? So we can use this equation to make these probabilities that are much better than the probabilities we got before on page whatever it was. We got those crazy probabilities. So now these are the same ones we got before. On page 171, right? But they're going to be different now. They're not going to be negative or crazy. They're going to be much better estimates, even in the middle here. So let's see how to do it. All right. So what we're going to do here, so you can say, why don't we say compare, these are going to be much better, to page 171. So I say, okay, so we start with what we have here, this and this, right? And so what do we have? Let's look at that. So we'll start with the log odds. We'll do it in steps. The first step is the log odds. So we have the predicted log odds right here, and that's this. I should have a little hat for predicted. The predicted log odds is equal to negative 12.2 plus 1.276, right, times 10. And I got 0.56 there. Okay, so now, to get the odds, what do you want to do? To get the odds, you just want to anti-log both sides. So to get the odds, so we'll just say e to the 0.56. And that's equal to 1.75 odds. All right, and now we just want to get the probability. So the probability, we know, is odds over 1 plus odds, right? If you forget that, you can just do it intuitively. You just remember, just think. You just do it like this is success. Think of it this way. And that is total, right? That's failure. Odds is success over failure. And now we want success over the total. So if you just forget that, it's just super easy to remember. So you want 1.75 over 2.75. And I got 0.636, or 63.6%. Okay, so you don't really have to memorize that. If you just memorize odds of success over failure, and you know the probability of success over total, it's pretty obvious. Okay? All right, so you can do these. Should we do these two the same way? Just to show you that we're going to get probabilities, you'll see that you're not going to get a negative probability or a probability over 1 here. Do you want me to go through it or not? Raise your hand if you want me to go through it. The 3 steps again? Okay. All right, so we'll just do it with the 6. So here, for the first one, we'll just say the predicted log odds here, and we'll say negative 12.2 plus 1.276, and this time it's going to be times 6. And what do you think we're going to get? We're going to get certainly something less than 1, so our log odds is going to be less than 0. So you get a negative number, right? And then our odds will be less than 1, and our probability will be less than 50%. So the odds is equal to e to the negative 4.544, which is 0.0106, right? And then our probability, step 3, is going to be 0.0106, that divided by 1.0. Just add 1 to that, 1.0106. So it's a small probability, and I got 0.0105, or 1.05%. And so for 14, I'll just tell you the answer, and you can do it on your own. And the answer I got, instead of something crazy over 1, I got 0.9965, or 99.65%. So you can just do that and check that you get that. Okay? Does that sound good? All right. So now, any questions so far on how you go back and forth between these? So you can only figure it out in the log odds, then you exponentiate, and then you just change the odds to the probability. All right. So now, what biological science score? What would you have? Would you get a 50-50 odds of getting in, of getting accepted? So we just want to solve for the biological science score. All right, so 50-50 chance. The equation we want to use is that, right? That's a linear equation, but that's in log odds. So 50-50. So if we have a probability or an odds of 50-50, or probability equal to 0.5, that means an odds equal to 50-50, it's 1, which means a log odds of what? Right in the middle there, e to the 1. I mean, the log of 1, sorry, 0. The log of the odds is 0. E to the 0 is 1. All right, so that's what we have. And so how are we going to do this? We know the log odds is 0. So now if we know that's 0, we can solve for the biological science score, right? So now we know that's 0, so we can just say the log odds is equal to 0, which is equal to 12.2 plus 1.267 times the biological science score. So that means that the biological science score is what? 12.21 over 1.276, which is 9.56. Okay. Any questions on that? So let's see how we can interpret the slopes in the log odds equation. First off, the sign of the slope indicates whether, if the sign is positive, that means the probability is increasing as x increases. If it's negative, it means it's decreasing as x increases. And the steepness, the magnitude of the slope, is going to indicate the steepness of the curves here. And notice that the log odds, that the probability curve here, the slope changes. It starts off, it gradually rises, and then it rises very more steeply, and then it gradually rises again. So it's steepest in the middle. So now there's these three equivalent forms of the logistic regression equation right here, and we have these three forms: the log odds or logit form, the odds form, and the probability form. And this one is just the equation for a line, right? So we just have a line right here that goes from positive infinity to negative infinity. And here we have an exponential curve like that. It goes from 0 to positive infinity. Or it could go, could be like exponential decay going down like that, but it's still from positive infinity to 0. Or we have this S-shaped curve up there, and it can just look something like that. And that goes from 0 to 1. All right, so now the odds form, this one, yields the most intuitive interpretation of the slope. So you'd think that this would be the most intuitive interpretation of the slope right here, because here we have a line. So this means that for each extra point in X, in this case your biological science score, that means that the log odds increases by 1.276. That's just that's just right here. That just means that the log odds just changes. This changes by a fixed additive amount, the way slope usually does. That's very easy to interpret as a slope, but people don't like to think in terms of log odds. It's not intuitive to them. So for the odds form, here what do we have? We have that in the odds form, it means that for each extra point on the X, in this case the biological science exam, the odds of getting into med school are multiplied by e raised to that power, e raised to the slope here. So e to the 1.276, which is approximately equal to 3.58. And that's called the odds ratio. The odds ratio is e to raised to the power of the slope. Okay, and so what is that? Well, that means that's a multiplicative increase in the odds for a 1 unit increase in X. So this means if you go up 1 point in your biological science score, you're going to multiply your odds of getting in by e to the slope. So, so let's see how we can use that odds ratio to compare the odds of individuals with different X values. All right, so let's do that. And so here are the three forms. And here are the three forms of the logistic regression equation. Okay, so here's the log odds. It's not the three forms. Here's the log odds equation, and we can change it into, we can exponentiate it to get the anti-log it to get the odds, and then to get the probability, we can say odds over 1 plus odds. Okay, so now let's say we were comparing the odds and probability of getting accepted for the following individuals. Let's say we knew, so somebody has a biological science score of 10, and if they go up 1 point in that to 11, well, then their log odds are just going to go up by, just adding 1.276. And their odds, how are they going to change? They're just going to change by the odds ratio. We just multiply that by the 1.75 times e to the 1.276, because they just went up 1 here. So that's the odds ratio. All right, let's write that down. So that will increase. So the odds ratio is equal to e to the slope for right there. And we said that's approximately 3.58. Okay, so 1.75 times about 3.58, and you get 6.27. All right, so that describes how the odds change. But what about the probability? So remember, so if the odds are 1.75, that's like the odds are the probability of success to failure. So you can think of it. You have a 1.75 times more chance of getting into medical school than not getting into medical school. So then when you want to look at the probability, you can just say 1.75, that's the probability of getting in, times the total number of outcomes. So if you think of 1.75 successes to 1 failure, it's 2.75 outcomes. And that's 63.6%. All right, so now when we go from the same thing here, so what would be the probability of getting in? Well, it's 6.27 divided by 7.27, and we get 86%. But there's no, so the odds, so if you, this odds ratio is useful because you can just going from, it tells you it's a fixed rate multiplicative factor in going from, for a 1 unit increase in your x, but there's no equivalent fixed factor that can describe how you increase in probability. So that's why people like the odds ratio. So for example, let's say looking from the chain, let's say somebody has a biological science score of 14. Well, you could take this 6.27 here, or you could start back here at 1.75. It really doesn't matter, 1.75. And then you would just multiply by that same factor, the odds ratio, e to the 1.276. You'd have to multiply it. If you're going from 10 to 14, you'd have to multiply it by that 4 times. So that's the same thing as saying times 4 up here. And that's equal to 288.2 times the odds. So that's a high B biological science score. And so you have 288.2 times the success to failure. That's your, that's the odds of getting in to not getting in. And so then if you want to look at the probability, it's 288.2 over 1 plus, adding those two together, over 289.2. And it's 99.65%. But there's no comparable way that we can directly go from, that we can describe going from knowing this probability to getting that probability without going back to the equation. So now let's say if we wanted to just go up, so you can see a 1 unit increase, no matter where you are in your biological science score, a 1 unit increase is going to multiply this, so you multiply this 288.2 by that same e to the slope, which is about 3.58. And that gives me 1,302.41. That is the odds. And then to get the probability here, you just say divided by 1033.41. And so that's going to be 99.9%. So there's no easy way to describe that. And if you think back over the curve, you can see that back here, right here, that you can see what we're saying is that that the odds is changing by a fixed multiplicative factor, right? The log odds is changing by a fixed additive amount here, right? But you can't describe the probability as changing by any fixed amount because it's changing here. The slope, look, it starts off gradually, then it rises steeply, and then it goes gradual again. Okay? So that's the idea why the odds ratio is useful. So this, that's the idea there. And now, let's look at our the last two problems here. All right. So two people have a 2-point difference in their biological science score. Compare their odds of getting into med school, given our logistic model. So the person with 2-point higher score has what one of these times greater odds. Sorry about that. This should be odds of getting it. So what would you choose here? Well, if they have a 1-point difference, they have e to the slope right there. And then for each and a 2-point difference, you just have to multiply again. So this is correct. And since for rounding, we said this is the same as 3.58, so of course this rounded within rounding error is the same. So either of those are okay, but these aren't. So don't make that arithmetic mistake and think those are equivalent somehow. All right, now let's just repeat. What if we have a 3? Oh, by the way, what if it was reversed? What if I said the person with a 2-point lower score? Well, then they would have what? You could either put negatives here, or you could just divide, or instead of multiply, you would divide by. You would have a 1 over 3.58 times 3.58. Instead of, right, that's pretty obvious. Okay, so now repeat with a 3-point difference. Okay, so the person with a 3-point higher score has what? Has what times greater odds of getting in? Sorry about that. So what would we do? We just take 2 points just multiply by the same thing again, right? So it would be e to the 1.276 times 3 up there. All right, and that is 46. 3.58 times 3.58 times 3.58. And if we reversed it, instead of we just say 1 over 46 times, if the person obviously, the person with the 3-point lower score would have a 1 over 46 times less odds of getting in. Now, if 2 people have a 3-point difference in their biological science score, how do their probabilities of getting into med school compare? Well, as we saw, it's hard to describe in general how they compare, right? Because we know we don't have enough information. Not enough information. What would we have to know? We'd have to know their biological science score, right? Because the probabilities and even the comparing probabilities, because any comparison of probabilities depends, because any comparison of probabilities, not to mention the probabilities themselves, but any comparison of probabilities even, depends on X, on the biological science score. Remember, what I'm saying is this. There's no easy way to just describe the change, to compare them. Because if you compare them up here versus here, it's going to be very different. Whereas if basically, when we know the odds ratio, right? When we know the odds ratio, but that doesn't mean we know the odds or the probability. But we don't know the odds or probabilities, or even the ratio of the probabilities. Okay, so that's the idea of the odds. And particularly, like we just talked about, like look at these probabilities. It's so easy to remember this, that when a 3-point difference in the middle in terms of probability is going to make a much, much bigger change than a 3-point difference here or here. And that's an easy way to remember that, okay? Does that help? Just remember that. It's so easy to see. And if you know probability, you know odds. because probability is just, you know the probability, just divide by 1 minus p, you know the odds. And vice versa. But the odds ratio is something else. That's different than the odds. Knowing a ratio is different than knowing the odds itself. So you know the ratio between the odds. You know the multiplicative factor that you multiply, but you don't know the change in odds. Okay? And this is easiest to see. All right, so that's it. And I should post your homework right away. And let's see what, and then we did a lot. And we have a lot of time left, so you can talk to me if you want. But goodbye. Have a great weekend. Thanks.